So this is the third lecture on the hydrogen radial solution. So continuing with our radial equation, just to remind you, remember we said psi was a function of r, theta, and phi, and we combined the theta and phi to give me these spherical harmonics. And now we're just dwelling on the radial equation, and now, since the radial equation is the only one that has the u in it, we're going to put in the u for the hydrogen atom. Okay, so that's where u was. It was E minus u. But now, last time we said, okay, we went to the S states. S states is L equals 0 states. So we could throw that out. And then we looked at the one with the least amount of wiggles, and we guessed it to be this, and this worked out. It solved this equation. And we also got the energy for that. There was the eigen function, there was the eigenvalue, and it just happened to be exactly the same thing we got for the Bohr ground state. Right. Okay, so really, what about all the other states right here? You notice up here, you're going to have more and more wiggles right here. And what that's going to do to this, to add the wiggles in there, you're just going to multiply this by a polynomial, some other constants to normalize it right here. But in general, r sub r is going to depend on how many wiggles right there, and the equation then comes down to be r sub r is equal to, actually before I get the r, let me look at the energies. What about the other energies right here? Energy is going to depend on some radial quantum number, which we could call it n sub r, and it's going to depend on L because L is in this equation, the other quantum number. So before I get the radial, we'll get the energy. The energy for all the other orbits right there, you notice it's going to depend on this radial quantum number, which we haven't got yet, plus this L quantum number, n sub r, say, and it's also going to depend on L, and it comes down to be just this same thing, minus me to the fourth, all over 2 times 4 pi epsilon naught squared, 2 times 4 pi epsilon naught squared, h bar squared. But then what we're going to have is 1 all over nr plus L plus 1 squared. So remember with the Bohr, it was just n squared. But now we're going to have an n sub r plus L plus 1, where n sub r we could say is the radial quantum number. N sub r is the radial quantum number. And it goes from 0, 1, 2, ... Okay, and you'll notice for our first case, the case that was over here, n sub r was 0. L was 0, and so we just had the 1 there. That's why we ended up with just this right here. But we're going to do something else. We don't really want to work with this n sub r quantum number. What I'm going to do is I'm going to define just n, not n sub r. N is just going to be n sub r plus L plus 1. And we're going to call that the principal quantum number. Principal quantum. Principal quantum number. Okay. Well, that way, if I plug this up into here, this is just n squared, and it comes out to be exactly what we had. So it's only going to depend on n because, you notice once we plug it in there, they're not going to have any n r plus l's. So it just comes out to what we had before, minus m e to the fourth all over 2 times 4 pi epsilon naught squared times h bar squared n squared, which is exactly what we got for the Bohr, which was our minus 13.6 over n squared. So there was our energy right there. Now to get our eigenfunctions, we're not going to use the n sub r, we're going to use the n now. And so r is going to depend on 2 quantum numbers, n and l. This one will depend on l. And then first of all, you're going to have the normalization out in front, which is 2 all over n a naught cubed n minus l minus 1 factorial all over 2n times n plus l factorial. That's just the normalization constant out in front. Then we get something like e to the minus r over e to the minus r, except this one's going to be n a naught. For our case, n was 1 right here, because remember, the lowest this can be is 0. The lowest that can be is 0. So n really starts out at 1, 2, 3. So n is equal to 1, 2, 3, dot, 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 dot. Okay, so the case we were looking at was the n equal 1. That's why we had that there. Okay, now what we said is it's going to be this times some polynomial that gives you the wiggling right here. We needed this to make it die out at infinity, but there's some polynomial, and they call that a Ligure polynomial. L-A-G-U-E-R-R-E. Ligure, probably, polynomial. So that's why when they higher the order of the polynomials, the more wiggles it puts into it. And they use the letter L for the Ligure polynomial. And it depends on 2 numbers. It's going to depend on the n's and the l's right here. Okay, and so what we have here also is we have a 2r divided by n a naught to the l power. And then we have our polynomial, my L. And remember, it's a polynomial with x. And in place of x in that polynomial, we put 2r over n a naught. That's where you put every place you see an x in that polynomial. And those Ligure polynomials depend on 2 numbers. One is n minus l minus 1, and the second number is 2l plus 1. Okay, so that is the radial equation right here. And just also, you noticed right here, what's the biggest L can be? Remember, we said before, L is equal to 0, 1, 2, 3, 4. Well, the biggest L can be is when n sub r is as small as possible. Well, the smallest n sub r can be is 0, so L goes all the way to n minus 1. So it goes all the way to n minus 1. So, and you remember, m sub L went from minus L all the way to plus L. Okay. So these are our radial functions. That's just this part right here. So now, if we were to look at our states, so let's just say we have n and L. For n and L, the first one, the lowest one for n is 1. Well, what does that mean L has to be? Well, L goes from 0 all the way up to 0. So L can only be 0. We call this the 1s state. Well, I'll just write up here the state. It's 1s. That's the ns. Well, it's the nl, I should say. So nl. The L means it was the S state, the N was 1. Okay, so we call that the N1, the 1S state right here. That L, just that factor of L, which we said was N minus L minus 1, and the other number 2L plus 1, 2L plus 1, 2L plus 1. Okay, that L sub this is just 1. So we didn't even have it in our first state. We didn't have any Ligure polynomial. There was just 1. And so that meant the radial, we would call it R, 1, 0, because it's RNL. So maybe I should write it like that. I should write it as NL. So this would be R10 should just be what we had over here. It should just be this one right here. It's 2 over A naught, 2 all over A naught to the 3 halves, e to the minus R over A naught. Okay. Now, if we, before going to the next row right here, if we wanted to say, well, okay, what is this term right here? Well, L is 0, we already know, and so M sub L can only be 0 when L is 0. So let me put M sub L over here. This is everything M sub L can be, and it can only be 0. And then we can say, okay, then what's your full psi? If you add in, so this would be 1, sorry, that would be 0, 0, and this would be 1, 0. So my psi now, it's actually going to be a function of 3 quantum numbers, n, l, m sub l. So in this case, it's just going to be psi of 1, 0, 0. Okay, and that's just going to, remember, why this spherical harmonic for this case was just a constant, so it's just going to move it by a constant. This just becomes 1 over the square root of pi times a to the 3 halves times e to the minus r over a naught. So that's the full wave function for the ground state of hydrogen. It's for 1, 0, 0. That's the 1s state, but they don't have a label for the m sub l. Okay, that's not too bad right there. But now let's go back and get the next state up. How about the 2? And this can be 0 or 1. Let's look at the 0 state. This would be called the 2s state. Okay, and this term right here would have just been 2 minus x. Remember, it's just a polynomial, except when we plug it in here, we're going to replace the x with 2r over n a naught. Okay, and so r, so now we're on the R20 state, is 2 times 1 over 2a naught to the 3 halves times 1 minus r over 2a naught, r over 2a naught, e to the minus r over 2a naught, r over 2a naught. Remember, it's r over 2 because there's a 2 there. Okay, so there is, should have started this over further, but that goes to here. Now m sub l can be three things. M sub L could be 1, 0, or minus 1. But this much of it would stay the same right here. This much of it, so psi, so this would be psi 2, sorry, that's not right. This M sub L, we're only in the L equals 0 state, so M sub L can only be 0. When we get to the next one, it'll be 3 states, but M sub L can only be 0. And so this is the psi 2, 200 state. 200 state. And that is 1 all over 4 square root 2 pi a naught to the 3 halves times 2 minus r over a naught times e to the minus r over 2a naught. Okay, just change the constant out in front. Okay, probably because we're still at L equals 0. Now let's look at the case where this is 2 and this can be 1. We would call that the 2p state. Okay, and this 2p state, this is still just 1. 1. Okay. Okay, and now we got our 2-1 state, which is 1 over the square root of 3, 1 over 2a naught to the 3 halves times 1 minus, sorry, it's not that, times r over a naught e to the minus r over 2a naught. Okay, so that would be the R21, the 2p state. Now there's, for the p state, there are 3 m sub l's. There's 1, 0, and minus 1. So over here you could have a psi 2, 1, 1. This would be psi 2, 1, 0. And this would be psi 2, 1, minus 1. Okay, I don't know if I have all of those right here, but if we looked at the, say the 2, 1, 2, 1, 0, I have that one. That one was 1 over 4 square root of 2 pi a naught to the 3 halves r over a naught e to the minus r over 2a naught. And then you get a sine theta e to the, well, if this is, cosine theta. It's just cosine theta. Okay. This one, these two right here are going to be very similar. The only difference is the very end with the phi part. So this one, these two, I'm not going to write them both out right here, but this one is 1 all over 8 square root pi a naught to the 3 halves r over a naught e to the minus r over 2a naught sine theta e to the minus I phi. This one would have been the same, but it would have been e to the plus I phi. It'd be the same as that one right there. Okay, and we can just keep going on. I don't know, maybe I'll do one more here. How about the 3, 0, that would be the 3s state. Okay, the Ligure polynomial for the 3 would be 6 minus 6x plus x squared all over 2. So you can see the polynomial is going to be getting bigger, which means that this R30 state will be getting bigger. It's 2 times 1 over 3a naught to the 3 halves, 1 minus 2r over 3a naught plus 2r squared over 27 a naught squared e to the minus r over 3a naught. Okay, and likewise, on the other side, we would say m sub l can only be 0. So this would have been 0, and then you could say the psi 3, 0, 0. Psi 3, 0, 0 would look very, I don't know if I'm going to write it. It's looking very similar to this one, except for the constants out in front right here. And it's still going to have a quadratic term in there. So it's just going to get longer and longer. So now we know all of the eigenfunctions and all of the eigenvalues for the hydrogen atom right here. Now, you remember, so now, remember, what this equation is saying is when we do the energy operator on psi, we get our E times psi. And this, remember, psi is NL m sub L, and this was NL m sub L. And so now, since we measure the energy, that gives us the principal quantum number n, the energy. We also said L squared acting on psi, the same psi, NL m sub L equals, what did we say? We said it was L times L plus 1 h bar squared psi NL m sub L. So this will allow me to get the L quantum number. Remember, they share the same eigenfunctions. So when you measure this and then measure this, it doesn't mess this up. You can go back and get the same energy. You can go back and get the L again. And then we also had LZ on psi NL m sub L. And that equals m sub L h bar psi NL m sub L. So we could measure all three of these to get the three quantum numbers, and that way we know exactly, if we make those three measurements, we know exactly what state we're in. We know exactly what state we're in. Okay, well, let's say you have some mixed state, phi. It's a mixture of, how about 1 over the square root of 2 psi, let me just say the 1s state right here. So I don't care about what the m sub L is. 1s state plus a psi 2p state plus 1 over the square root of 8 psi 3s state. 3s state. Okay, and now we ask, well, let's say we want to know what the average energy is. Well, before I do that, I have to make sure that this is normalized. So I have to figure out what A is to normalize this. So what does that mean? This squared plus this squared plus this squared has to equal 1. So 1/2 plus A squared plus 1/8 has to equal 1 right here. Or move that over, a squared plus an 1/8 equals 1/2 equals 4/8. Or subtract out the 1/8, that's 3/8, and take the square root. So A is equal to the square root of 3/8 right there. Okay, so now I know what A is right there. So phi is equal to 1 over the square root of 2 psi 1s plus the square root of 3/8 well, I think I'll make it 1 over 2. Well, we'll leave it as a square root of 3/8 psi 2p plus 1/8, 1 over the square root of 8, psi 3s. Now, if we wanted to know what the expectation value is of the energy, expectation right here, well, what do we have? We have the probability of measuring the 1s state is 50%, 1/2, it's that squared, times the energy of this state. Well, that's just, what do we say? It's just this, minus 13.6 over 1, because remember, this n is 1, so it's minus 13.6 over 1 squared, plus the probability of getting this one is 3/8, times the energy of this one right here. Well, that's just where n equals 2, so it's minus 13.6 over 4. Minus 13.6 over, I'll just say 2 squared. And then the last one is plus 1/8 times, and that's for the third state. Well, that would just be minus 13.6 over 3 squared. Okay, and so this is, and you could factor out some stuff. I guess we could make this 4 over, and another 4 down there, and we guess we could factor out the minus 13.6 all over 8, and we'd be left with 4 plus 3/4 plus 1/9. Okay, and then I guess I got to get a common denominator here. Well, if I get a, this would just be 36 times 4. Maybe it's, I'll just leave it like this right here. There would be the average energy. Okay, and then if we wanted to get the expectation value of the L squared, we could do the same thing. It would be the average of the expectation of L squared. It would be 1/2, just like we had before, except times the value you'd get. It'd be 1/2, and the value you'd get for this state is in the S state, that's L equals 0. For L equal to 0, L equal to 0, it's right here, L equals 0, you get 0 right here, that's 0, so you get times 0. Plus, the next state right here is the P state, that's L equal 1. L equals 1 is 2h bar squared. 2h bar squared times that probability, which we already said was 3/8. Plus, and then the third one was the SP, that was an S state. Since that's an S state, that's back to L equals 0, so that's 0. So you got 1/8 times 0. Okay, well, these two are gone right here, and that just is 3h bar squared over 4. 3h bar squared over 4. Now, if I knew what the m sub L were, I could calculate what this average LZ is, but I don't know that right there. Okay, I can also get our selection rules right here. Remember, the way we got the selection rules for orbital jumps, we called it this dipole moment matrix right here between an initial and a final state. I guess we'll say I and F. And so it would just be the integral from 0 to infinity, and you'd put R of the initial state, whatever the initial state is, star R times the final state, And then don't forget you need an r squared dr. Okay, now you're going to do this for each initial and each final state right here. And if you do this and you make a table like we did before, and this is the final state, which is 1, 2, I better space this out. 1, 2, let's say 3, 4, and this is the initial state, and sub I starts out higher, 2, 3, 4, and 5. What this does is it gives us how much it wiggles back and forth when you're in the mixed state right here. And this one right here, it's a distance. This one is 1.3a naught. That's the Bohr radius. This one was 0.51 a naught. This was 3 a naught. The next one up here is 0.3 a naught, 1.2 a naught, 5.4 a naught. You got to jump to a lower orbit. So this is a 2 to 1. It wiggles this much. 3 to 1, it wiggles that much. It looks like it wiggles a lot more from 3 to 2. And this other one up here is 0.21 a naught, 0.77 a naught, 2.25 a naught, 8.51 a naught. So first of all, you'll notice that you don't get any zeros in this. If I kept going, you wouldn't be any zeros, which means there are no selection rules for the n quantum number. We noticed that with the Bohr model. You could get all of the Balmer series, all the Lineman series. There wasn't any selection rules. We only have the selection rules right here for the L and the M sub L. That's all we have the selection rules for. Okay, so now we can go ahead and on the next one we'll start off with a energy spectra and showing all the states of the hydrogen atom. Okay.